Okay, hi everyone. Welcome to next seminar. So today we have Fred Hiskens coming at us from Melbourne. So Fred is a PhD student finishing up as we speak at the University of Melbourne, supervised by Ray Volkes and Matt Dolan. And he's done a lot of very interesting work of his PhD on using stellar evolution to constrain weakly interacting light particles like axions and dark photons. And I think Fred has done some quite important work and really knows his stuff when it comes to stellar evolution. And he's going to be telling us all about this interesting work today. So thanks, Fred, for being with us, and I'll leave it in your hands.
Okay, thanks so much for the introduction, Kieran. As Kieran said, my name is Fred, and I'm in the last few months of my PhD at the University of Melbourne. So today I'm going to be talking about some of the work I've been doing over the last few years with my supervisors, Matt Dolan and Ray Volkes. And I've called the talk "WISPers from the Stars, Advancing Stellar Constraints on Weakly Interacting Slim Particles." And so I thought I'd start by just having a look at the different elements in this title here, starting with WISPs, or the so-called weakly interacting slim or slender or sub-EV particles. And so really this WISP is just an umbrella term describing a collection of different light, feebly interacting dark matter candidates with a unifying characteristic that they must be non-thermally produced in the early universe in order to constitute viable dark matter candidates. And so, as Kieran said before, examples include the QCD axion, which famously provides the solution for the strong CP problem, more general axion-like particles, which share some of the interactions of axions, but don't necessarily solve the strong CP problem, and also dark or hidden photons, which are gauge bosons associated with new dark U1 gauge groups. And so the other element of my talk is obviously this notion here of stars, and the kind of connection between the two is that where the kind of characteristic light masses of WISPs makes their production kinematically accessible in many astrophysical systems, including stars. And so just the sheer size of typical stellar systems means that despite only having feeble interaction strength with standard model particles, WISPs can nevertheless be produced in great quantities in stars, and this can alter standard stellar evolution in a potentially observable way. So constraints based on this principle have existed since the 1980s. However, there have been since that time advances in observational and theoretical astrophysics, and then some combined with some known problems with some of the existing bounds, which really set the stage for these limits to be advanced. And this is the exact work that I've been doing over the last few years. So I do think it's worth pausing here to just quickly cover why we should be interested in doing this advancement. And so to this point, I think we should remember that the WISPs I've mentioned, axions, ALPs, and dark photons, particularly the QCD axion here, are the targets of numerous experimental programs, including helioscopes, haloscopes, light shining through wall experiments, and even direct detection. And the interesting point here is that the stellar constraints on these particles live in exactly the same neighborhood of parameter space as some or all of these experimental efforts. And so robust bounds from stellar evolution can complement these searches, or far more speculatively, but it's also important to remember if there were some kind of discovery, it would be important to understand any potential astrophysical ramifications of those. So by way of structure, I'm going to start the talk with a prologue, which covers the kind of what and hows of advancing stellar constraints on WISPs, i.e. answering the questions, what are WISP stellar cooling constraints and how can we advance them? And then I'm going to speak about two of the bounds that Matt, Ray, and I have developed over the last couple of years. So starting off with an updated limit on the axion-photon coupling, which is based on the paper Advancing Globular Cluster Constraints on the axion-photon coupling that was published in JCAP in 2022. And then in the second part, I'll discuss some more recent work from this year, which establishes updated stellar limits on dark photons. And this is based on the paper Constraining Dark Photons with Self-Consistent Simulations of Globular Cluster Stars, which we uploaded to arXiv in June. So with that said, yeah, let's get into it. So kind of in that little introduction before, I really asserted that WISPs can affect stellar evolution, but I haven't actually specified what the mechanism behind this is. So I'll start with that. So should WISPs exist, they could potentially be produced in deep stellar interiors. And if they're sufficiently light and weakly interacting, instead of being reabsorbed somewhere inside the star, they just freely stream out of it and therefore constitute a new source of energy loss from that star. So the response of a stellar region to energy loss of this kind depends on what kind of processes are occurring within it. So on the one hand, say if that region was undergoing nuclear burning, then the region responds to the energy loss by contracting and heating. And so in particular, this increase in temperature drives up the local nuclear burning rates, and which in turn means you accelerate the progression, or rather accelerate the consumption of nuclear fuel, and therefore the progression of the entire evolutionary phase associated with that period of nuclear burning. And so this can give you a constraint. On the other hand, if you have another region of the star which is not undergoing nuclear burning, for example, you could consider the degenerate cores of red giant branch stars, then these simply respond to the energy loss by cooling. Their temperature decreases. And this can also have potentially observable effects. For example, you could delay the onset of the next nuclear burning phase, and this can also lead to a constraint. So the general mechanism that I've just illustrated here is called the energy loss argument, and constraints generated using it are called stellar cooling limits, even though they don't necessarily involve the decrease in temperature of stars. So yeah, this energy loss argument has been used over the years many times to provide constraints on WISPs. And generally speaking, you can distinguish these constraints in two different ways. So first of all, you could ask, what are the evolutionary phases being targeted? And so there are many examples of this. So on this kind of left-hand trajectory that I pointed out before, we have bounds from the sun, horizontal branch stars, which are low-mass helium-burning stars, and also Cepheid variable stars. And so these are like more massive stars, which are a standard candle of cosmic distance measurement. For the right-hand trajectory, we also have bounds from red giant branch stars and white dwarfs. And so the other way we could potentially distinguish these constraints is via the different computational techniques they employ. And this starts from the kind of simpler ones, which are static limits. The idea here is that you would take a radial profile of a star at a single moment in time and just integrate the new energy loss across that radial profile, enforcing it to be less than some numerical upper limit. Then you can go to the more computationally intense way, which is to use stellar modeling. And so this is where you would iteratively solve stellar structure equations in one dimension, including the energy loss to WISPs within that model. So it's self-consistent and you can track the effect over the evolution of the star. And so actually already here, we've already kind of seen several ways, several of the hows for how we can advance stellar constraints on weakly interacting slim particles. So the first one is to note that this list I have in the top right-hand corner here is not an exhaustive list of the evolutionary phases that stars go through. So perhaps you could think, is there a way we can target other evolutionary phases? And the answer will be yes. The second way is to note that there are some bounds out there which are currently only static and would stand to potentially increase quite a lot if you bothered to go back through and do it with stellar modeling. And in particular, this is relevant for dark photons, which have typically in the past only really been afforded the kind of static treatment. And so we'll see this taking place in part 2. And the third one that's actually worth mentioning is over here. It's to do with this energy loss argument. And the general idea behind this one is, okay, well, these are quite well understood tracks for how you can lead to constraints. But what if there are other less obvious effects of energy loss that you could potentially use to build constraints? And so we'll again see that particularly in the second part today. So I do want to go through in a little bit more detail the first of the two hows I mentioned on the previous slide. The first one, of course, being targeting new evolutionary phases. And to do this, we need to first answer the question, what is the evolutionary progression of low mass stars? And so we'll have a look at this progression over here on a Hertzsprung-Russell diagram on the right-hand side. So this just plots the stellar luminosity against its effective temperature. Okay, so stars begin their lives on the main sequence where they burn hydrogen into helium in their cores, and this is the longest evolutionary phase. It can amount to about 80% or so of the total stellar lifetime. Eventually, though, the star will run out of its supply of hydrogen in its core, in its very center, and so hydrogen burning will continue in an off-center shell, and this shell will then surround an inert degenerate core composed of helium, and this is called the red giant branch phase, and stars are said to ascend the red giant branch. At a certain point, the conditions for helium ignition are met in that degenerate core of helium, and this ushers in the central helium burning phase, the horizontal branch, which I mentioned before. So here you have helium being converted into carbon and oxygen in a convective core, and this core is surrounded by a helium-rich region on top of which sits that same hydrogen burning shell, which is still burning during this phase. Eventually then, the supply of helium in the center of the star will also run out, and so this will usher in the second shell burning phase, which is called the asymptotic giant branch. So here you have an inner helium burning shell, and an outer hydrogen-burning shell, and both which surround an inert degenerate core of carbon and oxygen. And then eventually strong stellar winds strip away the outer layers of the star, leaving only that degenerate core and a thin layer on top of it, which goes on to form a white dwarf. So it's worth noting here, actually, that all of the phases I've mentioned on this slide appeared on the previous one as being targeted by WISPs, except for this one in green, the asymptotic giant branch. And this was curious to me because it's been known for a long time, in fact, since the late 90s, that this phase has quite good potential for providing constraints on WISPs, but it wasn't actually until 2021 when Matt Ray and I derived our first bound that anyone had actually produced a robust bound based on this phase. So the second tactic I identified on slide 2 that I wanted to mention was the idea of taking limits which are presently only static and re-deriving them using stellar evolution simulations. So I should note here that stellar evolution simulations have been the ubiquitous tool I've used in my PhD. So I do have to include at least a brief introduction to it, even though it is criminally brief, I'd say. So the main idea here is that under the assumption of rotational symmetry, stellar structure was governed by a set of coupled differential equations, the stellar structure equations. So these are, first of all, mass continuity and hydrostatic equilibrium, which are quite straightforward. Then energy conservation. So this tells you how the luminosity through a spherical shell of radius r changes as you change the radius. You'll recognize the first part of this as just the mass continuity equation. And then we have this parameter epsilon net here at the end. So this is the local energy liberation rate per unit mass. And it's given as a sum with positive contributions from nuclear burning and gravity, and then negative contributions coming from energy loss to neutrinos, and also energy loss to any new source you're putting in. And so this is the term that we want to edit if we're going to include WISP energy loss in a self-consistent way. And then the final equation we have is energy transport, and this can take a number of different forms depending on whether convection, conduction, or radiation are responsible for energy transport in that stellar region. So what you would do then is you'd supplement these equations with chemical abundance equations and then prescriptions for different micro and macro physical processes. So examples on the microphysical side include, say, nuclear reaction rates, weak reaction rates, equations of state, opacities. And on the macrophysical side, you have convection via the so-called mixing length theory, a phenomenon called convective overshoot, which I'll speak a bit more about in parts 1 and 2. That'll be relevant. And then also boundary conditions and diffusion or gravitational settling. So the idea here is that you would model the star as a one-dimensional array, where each cell in the model has well-defined thermodynamic parameters, and then just iteratively solve these equations with prescriptions for these phenomena to find the evolution of the stellar properties. And it's worth mentioning here that, as I'm sure you can imagine, our understanding of these processes here has increased substantially or improved substantially since WISP limits were first developed, and even over the last 10 years as well. So I should flag here that all the simulations you'll see all the results of the simulations you'll see in this talk were generated using the code modules for experiments in stellar astrophysics or MESA as well. So just to summarize then, our tactics for advancing stellar constraints on WISPs are to, first of all, target underutilized evolutionary phases, extend the computational rigor of limits on axions to other WISPs where this is necessary, search for variations of the energy loss argument, and a final one I'll put in is just to address any outstanding issues that are in existing limits, even if they're subtle. And so the first and the fourth here will be relevant for the part 1 of the talk, and then all 4 will actually be relevant for part 2. Okay, so on to part 1 then, advancing globular cluster constraints on the axion-photon coupling. And just to kind of signpost where we're going to go here, the structure of this part will be, I'll start by talking about globular cluster constraints on the axion-photon coupling. I'll then proceed to talk about an outstanding issue with these constraints before going on to tell you how we can advance them using something called the R2 parameter of globular clusters. Okay, so axions, as I'm sure we all know, are pseudoscalars, which are associated with the Peccei-Quinn solution for the strong CP problem. That is why the neutron electric dipole moment should be observed to be so small. It's a prominent dark matter candidate, and it's also the subject of numerous experimental searches, predominantly targeting their coupling to photons. So the limits that you obtain on axions, particularly on this axion-photon coupling, are usually visualized on the more general axion-like particle parameter space, and it's taken from Kieran's lovely GitHub page, in which the QCD axion models are confined to this band, the width of which is provided by the different ultraviolet completions for the axions. And so we're specifically interested in this region I've highlighted in purple over here. And if we zoom to a version of this parameter space from June 2022, going back in time a little bit, you can see that there are several bounds which are relevant in this region. On the experimental side, we have bounds from helioscopes like CAST and haloscopes. And then on the phenomenological side, we have cosmology, high energy astrophysics, and also stellar cooling. And so it's this one up here, the stellar cooling bound from the horizontal branch, or the R parameter, which we wish to advance. And the main reason that you could be interested in this is it's exactly this constraint which first constrains this QCD axion band. It's the one that crosses in this parameter space. Okay, so historically, the most restrictive stellar cooling bound on the axion-photon coupling comes from the R parameter of globular clusters, where globular clusters are just large gravitationally bound collections of old metal poor stars. And so this R parameter is the ratio of horizontal branch to red giant branch stars in those globular clusters. So because these globular cluster horizontal and red giant branches are populated with stars of approximately the same mass, about 0.8 solar masses, it means you can approximate R, the ratio of their two numbers, with the ratio of the two lifetimes of these phases, where these are the horizontal and red giant branch durations for a single stellar track or a single stellar evolution, simulation rather. And so what this implies is that observed limits on R can constrain the relative lifetimes of these evolutionary phases. So the way this bound works is, first of all, that axions are produced in these stars via the Primakov process. This is the conversion of a photon into an axion in the presence of an external electromagnetic field provided by the constituent charges in the stellar plasma. And this gives you an energy loss rate, which looks like this, where the main details I want you to take away are that there's this temperature to the power of 7 over density dependence. This function G here is a slowly varying function, which contains all the dependence on chemical composition, screening, etc. So the idea here is that for couplings of axion-photon couplings of about 10 to the minus 10 inverse GeV, the energy loss is efficient in horizontal branch cores, but not during the red giant branch phase, which means as you increase this parameter G10, you decrease the duration of the horizontal branch phase, but do nothing to the red giant branch phase effectively. So increasing G10 reduces your predictions for R, and then for high enough values, this will contradict observation, giving you a constraint. So this idea was kind of first introduced by Georg Raphael and Dirben in the 80s and was updated as recently as 2014, and into this exact version, which is the one appearing in the top right-hand corner here. And this all sounds fine, but as I've been trying to say, there is an issue here, and we'll discuss that now. So I want to give you a good explanation of this issue, and so to do this, I hope you'll permit me a quick little detour into the world of convective structure in horizontal branch stars, and we'll build up to it. And this first slide will contain a few definitions which are going to be relevant for both this part and also the discussion I want to have in part 2. So in stellar simulations, the stability of a region against convection depends on the relative magnitude of two temperature gradients, the radiative and adiabatic temperature gradients. Okay. Where the radiative temperature gradient is the temperature gradient a star would have if radiation alone were responsible for energy transfer. And this latter here, the adiabatic temperature gradient, is the thermal response of a convective element to adiabatic compression. And so I'll specify the exact form of the former because this is the one that's going to be relevant to the discussion I want to have. It's not a very pretty equation. The main things I want you to take away here is that it has this dependence, first of all, on the opacity kappa, but also the luminosity at radius r. These are the two things that will be relevant. And so according to the Schwarzschild criterion of stability, a stellar region will be stable if locally this parameter y, which is just defined as the ratio of these two temperature gradients, is less than 1. So with this in mind, the boundary of the horizontal branch convective core will simply be defined as the cell boundary in our model closest to the center of the star, at which y-1 changes sign. Okay? That's relatively straightforward, but as I've kind of been hinting at, the evolution of this boundary suffers from an intriguing problem. So formally, the convective boundary is defined at the location at which acceleration of convective elements falls to 0, but not necessarily their momentum. And so what this means is that convective elements here shown as these little gray circles can penetrate beyond the convective boundary and mix the products of helium burning, i.e. carbon and oxygen, across that boundary. And so this is that phenomenon of convective overshoot I was mentioning earlier. So it turns out that carbon and oxygen are more opaque than helium, which means that this mixing will actually increase the kind of opacity in this region just across the convective boundary. From the equation we had on the previous slide, we know that increasing the opacity means you'll increase the radiation temperature gradient. And so this will, and so what this can potentially do is if this causes that parameter y to become larger than 1, this region will also become unstable and the core will grow. Okay. It also turns out, though, that because we've taken a region which was rich in helium and made it convective, that helium gets mixed around the rest of the core. And so because this is less opaque, that'll lower the radiation temperature gradient profile as well. And so even though the core is growing, on average, the profile of this gradient is falling, and eventually it will fall far enough for y to go below 1 somewhere within this core, which causes the core to split. And so basically what happens is you have repeated episodes of this growth and splitting, which cause the convective boundary to become unstable. And so this sources stochastic and theoretical uncertainty. And crucially, this has been ignored in previous bounds. So it's this we want to address. So I think it's going to be illustrative to see the stochastic and theoretical uncertainty in action. And so to do this, we need to specify a scheme for modeling convective overshoot. So I'm going to use one of them. It's called standard overshoot. The idea here is that you would treat overshoot as a diffusive process where your diffusion coefficients decrease exponentially with distance from the convective boundary. And the scale of this exponential decrease is set by a free parameter called the overshoot parameter, f_ov. And this is calibrated to observation typically. And so we can then take this, run some simulations in MESA, and examine the horizontal branch core evolution with this, using this scheme. And so to have a look at the results, I'm going to introduce you to a kind of plot which appears all the time in this astrophysical stellar literature. It's called a Kippenhahn diagram. And so these things have as their y-axis what's called the radial mass coordinate. This is literally just the mass interior to a spherical shell of radius star. Because this is a monotonic increasing function of radius, it's a perfectly good radial coordinate, and actually makes a lot more sense than radius a lot of the time because stellar radii tend to vary quite a lot between one evolutionary phase to the next, whereas the mass is a lot more consistent. And so the idea here is that you can use this coordinate to depict locations or extents of regions within the star. So for example, I have the location of the star boundary given as the blue line up here. Burning regions like the hydrogen burning shell and the helium burning core are shown in red, and the convective core is shown in gray here. Then as your x-axis, you have the progression of time. Here, this is given as the time since the 0 age horizontal branch, where the horizontal branch phase begins, measured in mega years. And so basically you can track the temporal evolution of stellar structure using these. I've also included the central helium mass fraction, which should be read over here on this right y-axis. The idea here is that this enables you to track the progression of this phase because it's the central helium burning phase. This thing should decrease and go down to effectively 0 as the phase progresses. Okay, so with this in mind, we can make some observations. And first, I want to concentrate on this convective core. So as you can hopefully see, initially, the core kind of goes from a radial mass coordinate of 0 up to about 0.13. And so initially it grows outwards and outwards and outwards until this threshold at about 12 mega years through the phase, where it starts to vary up and down very quickly. And this kind of continues through to the rest of it. And so this is exactly that instability I was mentioning before. We have repeated episodes of growth and splitting. And so that's the one thing. We can see that instability. The second thing I want to draw your attention to, we can actually see if we have a look at the central helium mass fraction. So hopefully you can see as we're going along, this thing is decreasing, punctuated occasionally by little upticks from this instability, but looks basically on track to end by about 90 mega years through the phase. However, at this point, there's this spike in the central helium abundance, which instead of resulting in the phase ending, actually extends it by about 10 mega years. So it ends up just shy of 100 mega years in length overall. So this is an example of an event called a core breathing pulse, a horizontal branch core breathing pulse. And so I do want to explain what these are because it'll be important. So the main bottleneck for helium burning near the end of the horizontal branch is just the supply of helium in the core. There's not much left, basically. And so to compensate for this absence, kind of in a similar way to how the energy loss argument works, the central temperatures and densities of these stars increase to kind of keep up the rate of helium burning. So any kind of core growth that you get at this point, however, because of this instability of the convective core boundary, will bring additional helium into a core that's starved of nuclear fuel. And so what this does is it sparks an intense burst of nuclear burning. This in turn seeds the convective excursion deep into the helium-rich zone. and which brings back quite a large amount of helium to the core and extends the phase by some largish amount, say like 10 megayears in this case. The unfortunate fact is that core breathing pulses like this are not computationally stable. So what I mean by this is that their frequency and duration vary with the adopted temporal and spatial resolution in your simulation. And so what this does is it sources that stochastic variation in predictions for horizontal branch lifetime, and therefore R that I was mentioning earlier. And so we can examine what this looks like in terms of predictions for R as a function of the axion-photon coupling, basically just by running simulations in MESA with the overshoot parameter of 0.001, and then just repeating them 20 times each with different spatial and temporal resolutions. And so we build up this kind of distribution here. We have a region instead of just a line for our predictions for R. And so we can see that what in general what's happening is as you increase G10, your predictions fall, but there still is this range, which means you can't actually draw a constraint until your entire range of predictions falls outside the observed limits given by the black dashed lines. So then you can repeat this, yeah? Because F overshoot was just a model parameter, a free parameter of the model, we can repeat it, for example, increasing it tenfold. And what you see is we generate these new predictions in red, which are larger than those given the original one, and therefore fall outside the observed range at larger values of G10. So this kind of sets the stage to ask, well, which value should we take? Which one of these limits do we believe? And so just to summarize, these two features here that I've explained conspire to source both theoretical and stochastic variation of predictions for R, and we would want to address these if we were going to consider a bound like this robust. Okay. So fortunately, other globular cluster parameters exist, and these can be used to set complementary constraints on the axion-photon coupling. And a particularly strong candidate for this is the R2 parameter of globular clusters. This is now the ratio of asymptotic giant branch stars to horizontal branch stars in globular clusters. And again, these branches are populated by stars of approximately the same mass, so you can apply this rough relation here. And so some of the reasons we expect this to be good for us is that, first of all, the asymptotic giant branch helium burning shell, which is what governs this evolutionary phase, it is hotter and less dense than the horizontal branch core. And so we would therefore expect it to be more sensitive to axion energy loss than the horizontal branch core because of that temperature to the power of 7 on rho dependence I mentioned before. On the flip side as well, new, more statistically significant observed limits on R2 exist, and these had never been used to constrain BSM physics before. These were actually developed by a group at Monash University. And also just it's good to know that R2 has historically been used to constrain mixing across convective boundaries during the horizontal branch. So it seems like an ideal candidate for us. And so, yeah, we can have a look at this now in some simulations. So what we'll do is we take the simulations we had to generate these results over on the left-hand side, extend them through to the end of the asymptotic giant branch, and basically calculate R2. And so the results we get for doing that are here on the right-hand side. And so there are a few things which are worth commenting on straight away. The first one is that the effective varying convective boundary model parameters is opposite for the left and the right-hand side. So on the left for R, by increasing F overshoot tenfold, we had larger value predictions for R and therefore weaker constraints. On the right-hand side, we have the opposite effect. We have our predictions for R2 decreasing and therefore our constraint kind of moving down to lower values of G-stan. But at the same time, as I just kind of noted there, both R and R2 do decrease with increasing G10. And so this can you probably see where I'm going here. The idea would be for us to use these two against each other to come up with and be able to, and then marginalize over the uncertainty associated with convective boundaries or modeling them. It is worth noting, however, though, that R2 is actually more sensitive to low values of G10. And I grant you this is a little bit hard to see on this plot. So what I'll do is I'll take the two sets of results for this F overshoot equals 0.001, the two blue ones. I'll normalize them to their initial average values and then just superimpose them. So we now have the results for R2 in blue and the results for R in red. And as you can see, yeah, these ones for R2 do really drop down much faster for these kind of lower values of G10 than the equivalent predictions for R. So with this in mind, our goal is to calculate a bound on G10, which accounts for the sizable uncertainty related to mixing across convective boundaries. Our process for doing this is to start by picking a convective boundary scheme and a set of model parameters. For example, this F overshoot, we call this a realization of a scheme. You then simulate the evolution of stars given this scheme from the main sequence through to the end of the asymptotic giant branch for different values of G10, allowing for that stochastic variation as well that I was mentioning before. And so then you take those results and you compute implied limits from these data from R, but also R2, and then adopt the more restrictive of these as the limit for that realization. You would then repeat this for a number of other realizations of each of the available schemes in MESA and build up a kind of collection or suite of different constraints. So in the paper, and this took a very long time, we considered 20 plus realizations in total for 4 different possible schemes for modeling overshoot that were available to us in MESA. And actually what we found is that the limits from R2 were the more restrictive in every single case we considered. And so the most conservative of the limits we got implied that G10 should be less than 0.47. And this is nevertheless an improvement of about 30% over the existing horizontal branch constraint. That being said as well, the constraints we developed can be complemented by other studies of convective boundary mixing, for example, 3D hydrodynamic simulations, and there's been some work done there recently, or astroseismology. And in particular, the latter, astroseismology, favors one of the schemes we used, the predictive mixing scheme, and the limits from this scheme were between 0.11 and 0.34. So I do put them on the plot just to see kind of the level of improvement we could get, say, if these schemes would turned out to be correct. But just to be conservative, the final limit we stated was this 0.471. So to summarize, by appealing to the R2 parameter of globular clusters, we were able to set a new limit on the axion photon coupling, which was both stronger but also more robust than its predecessor. I was quite happy to be able to do that. So now I want to move on and talk about essentially the idea of taking those constraints we just developed from R and R2 and then applying them to another WISP, the dark photon. And so, yeah, we'll call this part advancing globular cluster constraints on the dark photon. Again, to cover structure, we'll start by talking a little bit about stellar constraints on dark photons which exist. I'm then going to speak specifically about some interesting effects that dark photons can have on horizontal branch stars. And when that's covered, we can then talk about the limits you get on dark photons from R and R2. Okay, so as I kind of said before, dark photons gauge bosons associated with new dark U1 gauge groups. They interact with the standard model primarily at low energy through kinetic mixing with the visible photon, which has the following low energy Lagrangian. Here F mu nu is the standard electromagnetic field strength tensor, and V is the equivalent for the dark photon. And so the parameter space of these particles is really defined by these 2 parameters you see here, the mass and also the kinetic mixing parameters, or kinetic mixing parameter rather. And so what this looks like, again, using the plot available here in GitHub page, is this. So clearly, you know, this is quite an inhabited parameter space by these different bounds. And one of the reasons for this is that, generally speaking, this can be subjected to a lot of the same constraints that are typically applied to axions and ALPs. So including on the experimental side, helioscopes, haloscopes, LSW, and also direct detection. And then on the phenomenological side, cosmology, but also our favorite, stellar cooling. And the stellar cooling ones are going to live kind of in this bottom right corner over here on the plot. And so it's obviously this which I'm going to be focusing on. So dark photon production in stars occurs when longitudinal or transverse photons, remember that in these kind of like hot, dense plasmas, stellar plasmas, photons can have longitudinal excitations, oscillate into the corresponding dark photon modes. And so the associated energy loss rates are given by this kind of formula here. So we have this factor G, which is a degeneracy factor. It's 1 for longitudinal and 2 for transverse. And then we have an integral over the dark photon energy loss. And it is worth pointing out we have this kind of, the lower terminal, and that integral is the dark photon mass. So really, I'm interested in the form of this parameter here, which is the dark photon production rate. And so this is given for longitudinal and transverse photons, dark photons by these following equations, which they're not great to look at. So we should point out this kind of gamma up here is the photon or plasmon damping rate, and omega p is the plasma frequency. So as I kind of said before, we shouldn't dwell too much on the form of these. I just want to focus on the fact that these production rates have a resonance conditions. And so for the longitudinal, production will be resonant when this term over here is very small, i.e. when the dark photon energy is equal to the plasma frequency in that particular stellar region where production is taking place. For the transverse ones, we have a different resonant condition. This production will be resonant where in the stellar region, which has plasma frequency equal to the dark photon mass, okay? And so these two different resonance conditions give rise to very different and unique energy loss profiles in stars. And so we'll have a look at what those look like now. So here we have the radial profile of a star. We've got the radial mass coordinate, a horizontal branch star, I should say. We have the radial mass coordinate down here on the x-axis. And I'm plotting here the log 10 of the plasma frequency normalized to 1 keV. So we should just note that, roughly speaking, the plasma frequency is set by the stellar density with some dependence on chemical composition as well. And so, yeah, it's really a decreasing function of radius, so as we can see, yeah, it kind of drops off the further out you go. So we'll play a little game now. What we'll do is I'll get you to imagine that this star is producing 1 keV dark photons. So dark photons with 1 keV, a mass of 1 keV, I should say. And what this means is that we can draw a black line here, which pinpoints exactly the stellar region where the plasma frequency is equal to the dark photon mass. On the left-hand side of this, you have a plasma frequency which is greater than the dark photon mass, and you have the opposite condition on the left-hand side. So the right-hand side, sorry. And so what we want to do here is we want to have a look at what the energy loss profiles to L and T dark photons look like. So starting with the L, I'm showing here again the log of the energy loss to longitudinal dark photons, here normalized to 1 erg per gram per second. And what we can see is that on the left-hand side of this boundary, this profile seems to pretty much track the plasma frequency profile. And this makes sense because this production is dominated by dark photons with energy equal to the plasma frequency, so that makes sense. On the right-hand side, however, we see that the production is suppressed. And so the main reason for this is that because the plasma frequency is less than the dark photon mass, this resonance condition is no longer included in the integral as showed on the previous phase. So you get this suppression. Then we can look at the equivalent form for transverse dark photons. And what you can see is that this energy loss is actually only really sizable in the region the stellar region which satisfies this resonant condition up here. And so this defines what we're calling a resonant production region, which is responsible for the vast majority of energy loss to transverse dark photons. It's important to note that this dominates over the equivalent longitudinal energy loss if such a region is present inside the star. And so it's worth me flagging that this kind of energy loss profile is pretty unique and atypical when it comes to typical stellar energy loss profiles. So first of all, because it's off-center, the peak is off-center, and also because this resonant production region will be free to move throughout the evolution of the star as the plasma frequency profile of this star changes. And so what this means is that the star could start off without not necessarily having one of these resonant production regions, but then acquire one throughout its evolution. And so I should flag here that because each phase of stellar evolution has a characteristic plasma frequency profile, this means that there will be a particular range of dark photon masses, which make transverse energy loss most relevant for that phase. So I've said before, stellar limits on dark photons do exist, having been derived, for example, from the sun, red giant branch stars, and the R parameter. However, these limits are static, and this is kind of what I was hinting at in the prologue. And just to remind you what that means, it means that they've been derived by, first of all, converting, say, existing bounds from axions or neutrinos to upper limits on novel energy loss, and then just demanding that the dark photon energy loss be less than this upper limit when either integrated over a static stellar profile or averaged over that profile, however you want to do it. And so the kind of claim I'll make here is that the reliability of static limits can only be guaranteed if dark photons affect stellar structure in a similar fashion to that of the original target of the constraint, the one that set this numerical upper limit. And so we're going to see in particular that for transverse dark photons, which again are produced in a resonant production region that moves, this is certainly not the case. So the goal going forwards is to use dynamic and self-consistent stellar evolution simulations to develop new constraints on dark photons from R and R2, and also the RGB tip, but I won't have time to really go into that. Yeah, and that's going to be relevant in this exact region of parameter space here, where transverse dark photon production is responsible for the constraint. And you can see here we have pre-existing bands from the horizontal branch and the red giant branch tip, but not R2, because that was more recent. Okay, So in order to derive limits on dark photons from R and R2, it'll be necessary for us to accurately characterize the impact that they can have on the evolution of horizontal branch stars. And if there's one key takeaway I want you to have from this, it's that the specific impact of dark photons will depend sensitively on where this resonant production region is. So we're going to examine these effects by considering horizontal branch Kippenhahn diagrams given 4 different implementations of this dark photon energy loss. So the first one was just no dark photons, no additional energy loss. The second one will be with a resonant production region far from the core. So this will be for 1 keV dark photons, just for reference. Then we'll have a resonant production region in the core during the horizontal branch phase. This corresponds to 2.5 keV dark photons, or ones with masses of 2.5 keV. And then one where the horizontal branch star doesn't actually acquire a resonant production region until very late in the evolution. And this is with a mass of 3.16 keV or thereabouts. So the first case, this is actually exactly the Kippenhahn diagram I showed you in part 1. We can see here that as the phase progresses, the central helium mass fraction gradually decreases, and this is punctuated occasionally by the instability of the convective core boundary. And then we have a single core breathing pulse occurring at the end as well. So the second case resembles this one quite closely, at least qualitatively. In fact, the only real difference is that, well, first of all, there is no core breathing pulse, but as I've kind of hinted, this is a stochastic process, so sometimes they don't occur. But the other difference is just that the duration of this phase has been reduced, basically. The total stellar lifetime, or the total lifetime of this evolutionary phase has been reduced, and this is essentially just exactly that application of the classic energy loss argument. Well, I should flag here as well, actually, that, again, we're showing the same information I had before in the Kippenhahn diagrams: nuclear burning regions in red, convective regions in gray, stellar boundaries now in dark blue, and I'm also showing the resonant production region, if it exists, as this kind of dashed yellow line here, its location. And the hatch to the end there shows you as well when the simulation is finished, because these are all set with the same x-axis scale, but obviously the simulations will be of different length. So then looking at what happens if you have a resonant production region in the core, you can see that, again, for the first part, kind of up to nearly 70 megayears, the evolution essentially qualitatively resembles this one. However, towards the end of the phase, it starts to suffer from very sizable and repeated core breathing pulses. So the net effect of this is that you go from a duration of just under 70 megayears to over 80. And then if we look again at the final one, we see that there is no resonant production region for a while, but then it does acquire one and then starts to suffer from these same very large and repeated core breathing pulses. And actually in this scenario, you'll notice that we have a duration, even though there is additional energy loss, we have a duration of this phase which is actually longer than that of the standard astrophysical case. And so this is very much at odds with that classic energy loss argument. I probably know what you're thinking. I've been kind of telling you before that this is a stochastic process. And so you could be wondering, well, could this just be a manifestation of that stochasticity? But no, actually, this is going to be evident even when you sample the stochastic variation enough. So we can have a look at that. In this plot, I've got the horizontal branch lifetime, again, allowing the stochastic variation to be sampled. And this is going to be shown as a function of different dark photon masses with a mixing parameter of 10 to the negative 15. And so the kind of range you get with no dark photons included in the model is shown in black. And what you can see here is that, yeah, initially it's kind of consistent. Then as the resonant production region heads closer and closer to the core, predictions for the lifetime decrease. But then actually they jump up again over the other side. And so these values you get up here correspond exactly to the final case I mentioned you before. And these are substantially larger than that you get just when standard astrophysics alone is considered. So what's going on here is really the question we want to answer. And to do this, we can consider the impact of the resonant production region on a horizontal branch profile. Okay, so such a profile is shown here. Again, the burning region is in red, the convective core is in gray. Basically what's happening here, and I should say that the total dark photon energy loss is shown in blue. Again, it's the log and it's normalized to 1 erg per gram per second. So what's going on here is that nuclear burning activity in the horizontal branch core is generating an outward moving flux of photons, basically. And we can quantify this as a luminosity. And so what you can see here is that as this flux moves through the resonant production region, many of the photons in it are resonantly converted to dark photons, and this manifests as a kind of step-like decrease in the luminosity. I should say again, this is the log of the luminosity normalized to one solar luminosity. And so what this does, because of our studies before of the convective structure of these stars, we know that a decrease in luminosity here should also decrease the radiation temperature gradient, and therefore this parameter y. And so this is exactly what we see. We see y just going down and then decreasing in this step-like function again across the resonant production region. Okay, so with that established, we can have a look at what happens next. So near the end of the horizontal branch, as I've kind of hinted at before, the density profile of the star starts to shift upwards. And so what this means is that this resonant production region will move further away from the center of the star. And so eventually what it'll look like is something like this. Yeah, it'll be far enough out that the decrease in y that you get over the resonant production region from the decrease in luminosity is enough to take y below 1. And so what you have here is the resonant production region effectively defining the location of the boundary of the convective core. And so we can have a look at what happens as this evolution progresses. As the kind of central density increases towards the end of the phase, the resonant production region continues to move further outwards. And so what this does is it results in the growth of that convective core. Eventually what happens is that growth can cause it to move into the helium-rich region, which can then bring an influx of helium into the core, which, if you remember, is starved of nuclear fuel. And this is exactly the recipe for a core breathing pulse. I should distinguish here, though, that unlike standard core breathing pulses, which are caused by, that instability of the convective core boundary, which again comes from chemical changes in the core, this is literally just caused by the outward movement of a dark photon resonant production region. And so basically what we found here is that some kind of interesting interplay between the energy loss mechanism, or the additional energy loss, and the convective structure of this horizontal branch star. And so the question left to answer in the remaining time is how does this affect the limits you can get from R and R2? So to see this, we can generate constraints from R using almost the same process that I outlined in part 1. The main difference is that now the energy loss rate is a function of 2 parameters, the chi and also the dark photon mass. So we have an extra dimension to the parameter scan we perform. So find limits on chi for dark photon masses at regular logarithmic intervals between 500 eV and 2.5 keV. And the results of this are shown over here on the right-hand side. So I should flag that we didn't go beyond 2.5 keV because at this point, horizontal branch stars don't have a resonant production region, and we couldn't push any further to the left either because we actually found that kind of dark photon resonant production was disrupting main sequence evolution too much to generate a constraint from the evolutionary phases that come after it. So that's something we'd quite like to have a look at in the future, really. And so generally speaking, the results, at least on the lower edge here, they kind of resemble that of the previous bound. That's kind of the black line in the background. The main difference we have between that one and our results is for masses below 1 keV, where our limit clearly has an upper boundary. And so what's going on here is that dark photon masses in this range result in resonant production regions very close to the hydrogen burning shell during the red giant branch phase. And what this means is that you can no longer make that assumption that the red giant branch's lifetime is unaffected by novel energy loss, and it causes the constraint to lose efficacy as chi increases. Now we can have a look at the equivalent limits you get from R2. Again, we'll generate this constraint using a very similar procedure to part 1. And we would pick dark photon masses between 1 keV and 10 keV. This is chosen because dark photons to the left of this, this bound is outcompeted by R, and to the right of this, it's outcompeted by the bound from the red giant branch tip. So the impact of dark photon core breathing pulses is more conspicuous in this one. Specifically, we have a very strong constraint in this sort of region down here, which is kind of between 2 and 4 keV masses for the dark photon. And these correspond exactly to where you have a resonant production region in the core, which causes these core breathing pulses. And so that's good to know that we can use the R2 parameter to constrain this kind of interesting non-standard effects. For masses, you might notice as well, for masses larger than about 4 keV, a strong constraint is still obtained. And this is because here what we have is the resonant production, no resonant production region will exist in the horizontal branch phase. So its lifetime will be unaffected, basically, but there will still be one in the HEB phase. And this leads to a reduction in its lifetime by that classic energy loss argument, which gives you a constraint too. So then what we can do is we can take those constraints and we can supplement them with the additional one we had from the red giant branch. which yields the following combined constraint shown in purple here. As you can see, the red giant branch tip one is shown as the kind of the black dashed line we have here. And so it's really only the most effective over here past this kind of 10 keV mark. You also see that rather frustratingly, there's this tiny little triangular region where the bounds just don't overlap. Look, it's a bit irritating, doesn't look very nice, but I suppose it does mean that we were at least quite thorough with the parameter scan that we did. Okay, so with that said, I'll conclude. So hopefully I've shown you that stellar evolution has been a rich source of constraint on weakly interacting slim particles for decades now. Despite this, however, the improving observational theoretical capabilities out there make their advancement possible even now. And so to summarize what we did, we used the stellar evolution code MESA and the R2 parameter to set a new limit on the axion-photon coupling, which is both more robust but also more restrictive than its predecessor. And then also developed new limits on the dark photons from R2 and also the red giant branch tip, which included transverse dark photon production in stellar models. And this was done this is the first. We also noted for this that we have this great little interplay between the energy loss and convective structure. So thank you for attention.
Thanks, Fred, for that very stimulating talk. Let's have some questions. If anyone wants to go before me, please do. I see some applauses. Bruce?
So thank you very much for your talk. A question in some ignorance, since I'm not an astrophysicist. You were discussing the instability at the boundary.
Mm-hmm.
Since convection takes place on a scale smaller than laterally, on a scale smaller than that of the whole star,
mm-hmm.
and you're describing an unstable arrangement, do we need to worry about failures or departures from spherical symmetry?
In principle, yes, absolutely, you would. This is the awkward part about doing convection in stars, is that obviously the gold standard is to do one of these 3D hydrodynamic simulations, but these are incredibly resource intensive. It's hard to get time, it's hard to do them for astrophysical purposes, let alone BSM ones. So it's a great point. I suppose, like, ultimately, I think the only way to really tell what these things would look like would be to include it in those kind of 3D simulations. But the kind of criterion that's breaking here is a relatively straightforward, is a relatively first principles approach and should approximately be accurate, basically. And also the kind of splitting that you're seeing is on a large enough scale yes, basically there is large uncertainty going on here. The reason we have a lot of different schemes for modeling these things in these 1D simulation reflects precisely the fact that this is hard to model. And so this was our idea for marginalizing over those, basically.
Sure. I feel that there should be some sort of principled version of that argument involving scale sizes, time scales, energy budgets, or something like that, rather than saying 3D is hard and 1D is doable. Because
no, I agree with you.
I already understood both those points, right? But
yeah.
No,
I agree with you. I think I'm probably not educated enough on the intricacies of it as well. They may well exist, and it'll be interesting. I should really go and have a look and try and find them. But yeah, I imagine they do. A lot of effort is put into devising kind of approximations that work in 1D.
Right. And when it comes to modeling, there are techniques between 1D integration and 3D exhaustive simulation a la the Matrix. People have come up with techniques between those two.
Yeah, that's true.
Right.
There was some interesting work done recently, which was examining this sort of stuff exactly in those 3D simulations as well. And so, unfortunately, it wasn't quite in the stellar mass range, which was most pertinent to me. But so I'd love them to come back and do it in a different one. Then I could probably have some more concrete information to say. Yep. But it is. This is it's one of those things which is very well known in the astrophysical community that you have this instability, and therefore essentially what you should do is be conservative about it. But obviously this is a fact which a lot of BSM bounds will gloss over because it's an inconvenience, essentially.
Right. Yeah, I mean, 5 times as much work to do to add a bit of sophistication than to do the basic version.
Yeah, exactly.
Yeah. All right, thank you.
Thanks, Bruce.
Anyone else? If not, I will go. So maybe I'll start with the I think smaller questions. So that can you just clarify for the dark photon case? You talked a lot about the transverse mode and including where this resonant production region ends up. But are you still in the background including the longitudinal emission as well?
Yeah, I am. I can actually. So the way these constraints typically work is, when there is, I am including it, but when such a resonant production region is there, the transverse ones, the transverse production is essentially dominant over it. So the vast majority of the energy loss comes from it. So the typical shapes that these bounds have over here are kind of like, this is a prototype of what they look like. So you have this kind of, basically in red is the bound. So this is a bound from the sun. In red is the bound you get, and it's quite a straightforward one. In red, you have the limit you get using transverse energy loss only. In blue is using longitudinal energy loss only, and then you can combine the two, obviously. So the region here, where the transverse one is dominant, is precisely where you have a resonant production region within the sun. And so this is essentially the only region of parameter space we were studying when it came to red giant branch stars and horizontal branch stars and asymptotic giant branch stars, which is why I spoke much more about it. It's also because it actually kind of counterintuitively gives you the more interesting physics. And then kind of down here to the left is where the longitudinal is dominant. And that's actually because they have different scalings for the dark photon mass as well.
Yeah, that was actually why I was wondering, because your limits, they sort of, they stop at a certain lower limit in mass. So I was thinking maybe you were neglecting the longitudinal motion, but I think you said actually towards the end that you actually cut it off yourself because you didn't trust the evolution or something.
Yeah, that's exactly right. It was an interesting quirk in that, and this is inherent to when you're doing building bounds, which are based on looking at these kind of dynamic stellar evolution simulations. If you're disrupting an earlier evolutionary phase, can kind of make you lose some faith in what your simulation is telling you from the later ones, or it can even make getting to those later ones very time consuming. And so what we would like to do is come back and think of a nice way to use main sequence stars, maybe more than just the sun, to constrain that sort of region as well. And so that's kind of stuff we've started on now.
The other thing I wanted to know was, okay, maybe I'd stick with the dark photon first. Have you considered I don't know if it's significantly different, but these other dark photons, for example, like a gauged U1 baryon number or U1 B minus L, like these other cases that people talk about. Is it straightforward to just remap things to that case, or
I haven't really considered. Look, we spoke briefly about it. I would dare say there'd be implications for it, but I'm not sure how straightforward the mapping would be. So, and I suppose the entire point of this one is like when you have these resonances and stuff, you have to go over it with quite a fine-tooth comb to actually get everything. So I'd say maybe like assuming it would be counterproductive for assuming like an easy thing would be a little bit counterproductive for the kind of like the narrative of this work. So yeah, it could be something that's worth doing. Maybe it is. I would need to think about it a little bit more.
And then can you talk a little bit about the red giant tip?
Yeah, sure.
And why you seem to be quite a lot less constraining than the previous
so there are two things going on here. So this is what our red giant branch constraint looks like, kind of in the top right hand corner here. And so like clearly there are two differences that we have. One is that we constrain this kind of region here our constraint is a lot stronger in this region than theirs, but it's also weaker over on this right hand side. And so essentially what's going on here is basically we can work out what's going on here by looking at the evolution of the maximum temperature during the red giant branch phase, because the red giant branch phase ends and therefore has its maximum brightness at the moment where helium ignition is met and that has a temperature threshold, basically. So in the normal situation, you have neutrino energy loss to neutrinos, which moves the maximum of the red giant branch temperature profile off center. And so anything you do which further delays the increase in that temperature will further delay the ignition of helium, and therefore leads to larger luminosities. That's what's going on behind the scenes. And so basically these bounds are static, as I said before, they're one behind. So you can either do that by taking a snapshot of the star at a single moment, usually kind of just before helium ignition, and then integrating the energy loss over the top of that. Or you can just basically evaluate the energy loss with average core conditions for a red giant branch star. And so what this does is it basically just, you're blind to the effects of that moving resonant production region. So if we look at this case down here, I have in the bottom left, shows you the progression of the max temperature for this case up here. So for a dark photon of 3.16 keV and this kinetic mixing parameter. And what you can see is that as this phase progresses, the central density increases and increases, and then ultimately at some stage, still quite a while before the end of the red giant branch phase, the star acquires a resonant production region. And so it's actually here that you see the strongest departure in the maximum temperature from that of standard astrophysics. And so this is what then gives you kind of that decrease really compared to compared to the standard case, and what delays, and it ends up giving you a higher red giant branch tip luminosity. And so if you could imagine just like taking a snapshot of this star right at the end though, then the resonant production region will be really far out, like somewhere out here. And so it's possible that just by integrating energy loss, you don't really give it, it's not afforded much importance in that process. Whereas it's kind of this dynamic effect over here during the evolution that contributes most. So that's why our result is stronger in this region. In this kind of yellow one here, they're both pretty good, and you essentially have the same thing going on, but because this is acquired later, the resonant production region is closer to the center at that snapshot. So the final one, though, is also interesting. So basically what you have here is you have the star acquiring a resonant production region, but it essentially does so very late. It does so just before the phase ends. And so there's really not enough time for it to noticeably impact or decrease the maximum temperature. It'll certainly decrease the central temperature, but not the maximum one. And so you don't actually end up getting a decrease in the red giant branch tip luminosity, even though if you were just to integrate a standard static profile, that's what you would get a strong bound from that.
Yeah.
So that's essentially the spirit. That's what's going on, really. Does that make sense?
Yeah. Thanks.
Cool.
Yeah, the other thing I wanted to know is more of a general point that applies to most of the talk. So when you're talking about these ratio parameters, you wrote down the equation. The ratio is defined observationally as the ratio of the numbers, but then you were relating that to the ratio of the lifetimes.
Yeah.
I guess there will be some issue there potentially to do with like selection biases and whether you're really measuring all of the stars. Is that something you need to deal with, or is that something astronomers have already dealt with?
It's something that astronomers tend to deal with. Yeah. And so like essentially one of the ways, and you also have issues with like multiple populations and stuff there in globular clusters, which is always a kind of footnote that needs to be added in. So essentially what you can do here is that they're kind of like, and this is certainly what they like Ayala paper from 2014 did, is you basically exclude bluer. So like you can get different horizontal branches out there. You can get ones which are bluer, so hotter, and they tend to have a higher helium content. And then you get ones which are less blue, or redder. Okay, and so the idea is if you bias towards the ones which are redder, you tend to exclude ones with like multiple populations having an effect. Yeah, it's something which is really addressed at that kind of the observational level. But by kind of like picking only those red ones, it seems to handle a lot of the cases as far as I know. But it's a good point, yeah. And the approximation, I know I've got like the kind of twiddle sort of thing, but it is pretty good, really. The idea, how you would do a better calculation for this is to develop a set of isochrones, which are kind of like these perpendicular really to stellar evolution simulations. A stellar evolution simulation tells you how the properties of a single star evolve over time. An isochrone tells you the differences in properties of stars of different masses at a single time, so hence isochrone. You would use a set of those, which also come from stellar evolution simulations, and then like an initial mass function and something like that, and then build up kind of synthetic Hertzsprung-Russell or color magnitude diagrams and make comparisons with that. But then you're introducing uncertainty as well, from potentially introducing uncertainty from different initial mass functions, but it turns out that's not going to actually affect it very much because you're dealing with these ratios, and yeah, the power law doesn't affect it too much. So yeah, there's a whole host more you can do. That's kind of always the question here, or always the point here, but it tends to be pretty good.
Mm-hmm. How much is in general terms, like chemistry important for deriving or how sensitive are the bounds to the detailed chemistry of the star? I mean, for things like the plasma frequency profile, it depends explicitly, right, on the you know.
Yeah, so obviously more so it's more so in the dark photon case than it is in the axion case because of precisely this thing. Look, in terms of the axion one, there are a lot of systematic uncertainties you can take account of, but really these are all just sub-leading compared to that convective mixing, the convective boundary thing I was talking about. In principle, you do get changes to the plasma frequency profile, as I said before, for the dark photon case. They're not going to be too big. I don't have a number in the top of my head, but it wasn't that big. Essentially what it'll do is it will just like shift that peak marginally from side to side or something like that. Or the trough, rather, whatever you want to call it. Yeah. Mm-hmm. Yeah, I'd have to have a look at the numbers again to give you a more refined answer than
that. All right, so if anyone has any final questions, please go ahead. But if not, I think I'll